Well, welcome to this video. We were talking about the control and data plane separation. We already saw why it is important to separate the control and data plane, and we were talking about the challenges and possible solutions for those challenges when you separate the control plane from the data plane. So the main challenge that is actually visible when you separate control and data plane is the fact that normally one can think that the controller or the control plane is located in just one server. So there is a problem of reliability there, also a problem of scalability, and those are like the main challenges that you can think on when you think in a separated control and data plane. It's important to know that this is not actually real. The control plane is normally centralized in a logical way. That means that logically one central entity knows all the information of the network, the topology, and takes decision from it. But physically, it can be actually distributed. And we're going to see two controllers or two control plane approaches in SDN that actually tackles these problems of scalability, reliability, and consistency, RCP and Onyx. So let's first see the scalability challenge and how you can deal with this challenge in RCP. RCP is a first, let's say, separated control plane platform that is just based or just used for routing perspectives. So just routing is done with RCP. So it's SDN, but just for routing. It's not for traffic engineering or security or things like that. And it uses normal protocols. It does not use the standard OpenFlow protocols. It uses the BGP protocol to separate the control and data plane. So the problem in scalability is that RCP must store routes and compute routing decisions for every router. So you have the RCP controller here, and you can potentially have thousands of routers. So you have a lot of routes, and then the scalability becomes every time more difficult. So the principles to solve this problem in RCP is to, first of all, eliminate redundancy. So you store a single copy of each route, because you can get from different points several copies of the same route. So the idea is to filter this a little bit and make a single copy of each route. Also, you can avoid redundant computation by doing so, right? So in this way, you don't have to compute every time new routes as you first made a filter on that. And you just perform BGP routing. You don't use other protocols. So what you do in RCP, you calculate here the routing decisions without using any normal protocol like OSPF or RIP, but you can just implement routing algorithms there and make the routing decisions, and then via BGP or iBGP you can transfer these decisions to the routers if they are internal routers, and via eBGP you can transfer the decision to routers in another autonomous system. So it just uses BGP routing, and in this way, let's say the approach is more scalable. In Onyx, in contrast, you don't have one single replica of a controller. You have a set of replicas of the controllers, and you keep just a subset of the overall network information in memory. And you use a hierarchy in the controller. So one controller is, let's say, uh, one controller is taking, we can say that this is a controller and it takes care of this part of the network. This is another controller that takes care of this other part of the network, and this is another controller taking care of this other part of the network. And then you can have even hierarchy of the controllers where you have different parts of the net. You collect the information of all the networks in these controllers, and in this way you separate the information of the controllers and you make all the approach more scalable. So you can combine statistics and topology information with different part of the network. thinking on this as a whole network, right? Okay. In terms of reliability, which is very important, right? If we have a single point of failure, it's very difficult to have reliability. So you, in RCP, you make replicas. So you run multiple identical servers. So what you have is you have the network, right? With all the network here, and then you can have several RCP servers. RCP1, RCP2, and RCP3, and all the information of the network is collected by the servers. So they have the exact same information of the network, so that if one of the server fails, the other ones can enter, and they have the same information at the same state. So the replicas are actually independent, but they have the same information. Each replica has its own feed of routes. Each replica receives the same inputs and runs the same routing algorithm, so you will have always the same information there. And there is actually no need for a consistency protocol if both or more than two replicas always see the same information, right? So this is the idea with RCP. In contrast, if we talk about ONNX, ONNX assumes the reliability in another way. It says that if the failure is in the network, then it's an application responsibility. But if the failure is in the connection to the ONNX controller, then it ensures a reliable protocol with multipath and so on. So you have an ONNX controller here controlling one part of the network, right? So it ensures that it has multiple paths to acquire the information from the network, so that if one of these links, or let's say paths to the ONNX server fails, then the information can come from another source, right? From another path. If you, in ONNX, as I said, we have different replicas, and if there is a failure, so you have distributed coordination of the replica. So for instance, if this replica is taking care of this part of the network, this replica is taking care of this other part of the network, and this one fails, then they have a distributed protocol among them, right? So they inform, for instance, this one that it will also take care of this part of the network. And in this way, you ensure reliability. You have replication algorithms and strategies in ONNX with a network information based, represented as a graph of objects, where you have all the applications, let's say the SDN applications, can read and write in the, let's say, in this network information base, which has all the information of the different replicas, and it can automatically update switches and controllers in this way. It actually uses state distribution tools, right? Replicated transactional SQL storage with a strong consistency for critical stable state, and one hop memory-based distributed hash tables for, let's say, less critical dynamic state. So then you have mechanisms to perform replication, and in this way ensure reliability. So this is just an example of two controllers that are actually kind of distributed to cope with the normal, let's say, shortcomings that you can see in SDN. So these are actually not the only distributed controllers. There are a lot of distributed alternatives, like also Open Daylight and ONOS. We will see a little bit more in the controllers in upcoming videos. Now we pass to a very important part of the SDN architecture, and it is the OpenFlow protocol. This is the, let's say, a standard or de facto, let's say, standard of the southbound interface, or the interface between the data plane and the control plane. This is data plane, and this is control plane in SDN. So this interface between these two is de facto OpenFlow. So it is a protocol which has a specification, and an OpenFlow control plane communicates with a data plane or a switch over a secure channel using the OpenFlow protocol. The OpenFlow protocol defines the message format of this communication. The purpose of this protocol is actually to update the flow table in the switch. So you have a flow table in the switch, and all the logic is of course executed here in the control plane. So in the switch, actually, if you have an OpenFlow enabled switch, you have a flow table that performs actually packet lookup. All packets are compared to the flow table for a match. So you have different entries in the table, and you extract the header of the packet to see when this packet match or what entry this packet matches. And the actions, then each time the packet matches one entry, it performs an action that depends on the match. If there is no match, traffic is sent to the controller. So it is a secure channel between the data plane and the control plane. If we go here, this is let's say the flow chart of the OpenFlow protocol. The packet enters in the network. This is optional, just for span entry processing, but it enters in the network. Then the switch will parse the header of the packet, all the fields of the packet, and it will go to the tables, the flow tables that you can find in the switch, looking for matches. If there is a match in one of the tables, it applies the actions that correspond, or the action that corresponds to that match. And if it doesn't match, it sends the packet to the controller. The packet header fields are matched against one of n tables. If there is no match, packet is sent to the controller. Otherwise, the switch performs the predefined action. What are the fields to do the matching in OpenFlow? Let's first look at OpenFlow 1.0. The first version of OpenFlow is the one that we're going to actually use in this course, as it is the first one. And to introduce SDN, I think is the best OpenFlow version to look. Anyway, we will work also a little bit with 1.3 version. So we have the OpenFlow controller, the OpenFlow protocol, and here in the switch we have the flow table. In the flow table, we can do a match in any combination of this field. The switch port, so the actual physical port from which the packet entered to the switch, the source MAC address, the destination MAC address, the Ethernet type, VLAN ID, IP source and destination, the type of protocol, TCP or UDP, transfer protocol, and the TCP or UDP source and destination port. So you can do any combination of these fields to actually perform the match in OpenFlow 1.0. You have a 12 tuple with also VLAN priority and type of service. These are another two fields that you can use. And when you make a match, then you can do an action. The action can be a forward action or a drop action. If it's a forward action, so you have the packet and you can forward the packet with the old action, send the packet out through all the interfaces, but not the incoming one. Controllers, so encapsulate the packet and send it to the controller. Local, send to the switch, local networking stack, the normal switch stack. Table, perform actions in a flow table. This is also only for one type of packets that are called, one type of messages that are called packet out messages. We will talk about that in the coming classes. Import, so send the packet out, the input port, so let's say return the packet through the port from which you received the packet. Optional is the normal forwarding or the normal spanning tree of the switch. So you can do any of these forward actions or a drop action, which is actually drop the packet. You can also have the modify action, which is very used. It's an option to modify the packet header values in the packet. So you can actually modify the destination IP address or the VLAN ID or any field of the packet can be modified. So you can set VLAN ID priority, set destination IP address, whatever you want. Another one is in queue. You can send the packet to a queue actually inside the router. Okay. Now we go to the OpenFlow version 1.3, where you can where we can see some enhancements that were done to this protocol. In the version 1.3, you have the action set, which is that you can apply a set of actions on each individual packet. You can have the group, which is a list of action sets, and each table can update fields, or modify action sets. This is nice because there are new features that you can do here in this with these enhancements. For instance, the action sets is just to apply not just one action, but a set of different actions in one packet. You can actually execute with the groups all action sets in a group. For instance, for a multicast, you can clone the packet for each action set in the group, so you can have the same behavior in several clone packets for multicast purposes. In the indirect groups, you can execute one bucket defining the group. This is useful, for instance, to point multiple flow entries to a single or common action or set of actions. So for different entries in the table, you may want to do the same action or the same set of actions, so you don't have to define the actions each time, so you can just use the indirect groups. And new actions can be done, like, for instance, well, you can use actually MPLS in 1.3. You can apply MPLS push action to a packet in the switch. You can decrement or increment the TTL. And you can even in 1.3 apply QoS actions, like setting the type of queue that, or the type of queuing discipline that you want your packet to follow, or your queue to actually use. And these are good examples of actions. We will see more details on how to implement OpenFlow, match entries, or let's say flow table entries with match and actions in the coming classes. So other details of OpenFlow are that you can do actually metering and traffic monitoring. OpenFlow is not just to push, let's say, flow entries in the switches, but also it can monitor the behavior of the switches by receiving information from them. This is the metering and traffic monitoring part of OpenFlow. And the control channel details, you can set or configure the encryption that you want. And you can also say how to handle control messages from different or multiple controllers when you have distributed approaches in the control plane. So this was more or less the class and the information about separation of control and data plane. Thank you very much for your attention. In the next session, we will start with the emulator of SDN, that is the Mininet emulator. Thank you very much.